lesson 1.3, equations and graphs of polynomial functions. So we have a little warm-up here. We have a roller coaster. It's designed so that the shape of a section of the ride can be modeled by the given function. Okay, so you have a polynomial function there. It's fairly complicated, and this covers the first 60 seconds of the ride. So x values are time in seconds from 0 to 60. And the function gives us the height of the ride above the ground. So it's full of ups and downs at time x. Graph, that's just an example of something that we could talk about as far as polynomial functions and equations and mapping them. So what we're going to do, though, is graph an easier one. We're going to graph the quadratic function y equals x plus 2, x minus 4, and make some connections. Do you guys remember how to graph something like that?
It's in factored form. You got to simplify it.
It is in factored form. We could put it in standard form, but standard form doesn't give us much. We could put it in vertex form because it's a quadratic, and that would give us the vertex. But actually, we get quite a bit of information just from factored form. What do we get from factored form?
X-intercepts.
We get the X-intercepts. Okay, so basically, X-intercepts occur where y equals 0. So what values of x would cause this whole equation to equal 0? Well, if the first bracket were 0, if x plus 2 were 0, the whole thing would be 0. And if the second bracket were 0, that would be another option for an x-intercept. So here we use simple algebra. We subtract 2 from each side. We have an x-intercept at -2. Here we add 4 to both sides. We get an x-intercept at +4. Okay, so we have an x-intercept at -2, and we have an x-intercept at +4. What else do we know about this graph? What's the sign of the leading coefficient? Is it positive or negative?
So negative or no? Positive.
It's positive, right? So it's going to open up. So its vertex is going to be somewhere, it's symmetrical, so it's going to be right in between these guys. It's going to be somewhere down here. And we could, so it's at x equals 1. And we could figure out exactly where it is. If x is 1, then this is 3, and this is -3. So that would be down here at -9.
Where'd you get x is 1 from?
That's just the x value of the vertex. Basically, you just take the average of the two x-intercepts. So you have a vertex down here at 1, -9. And you have x-intercepts at +4 and -2. Okay, that's basically enough to help us get a sense of it. But what did we get straight from factored form? Well, we knew that it was a quadratic that opened up, and we knew its x-intercepts. So we can use that information to graph even more challenging polynomial functions. Factored form is going to be really helpful. It's going to give us the zeros. It's going to give us the x-intercepts every time. Okay, so let's move on to some notes. Hopefully you have enough space for what we're going to talk about. We're going to write a bunch of things. And it's going to match along with the picture there that you have. For the polynomial function y equals f of x. So basically, what does that mean? That means this is true for any polynomial function. Okay? The zeros correspond to the x-intercepts. The zeros correspond to the x-intercepts of the graph. So for every polynomial function, the zeros correspond to the x-intercepts of the graph, and the roots of the equation f of x equals 0.
How would you get the vertex?
For a quadratic,
Actually, no, there
you
is no vertex.
potentially,
Yeah.
right. Okay, so what do you have here? Basically, you have a sentence that says zeros, x-intercepts, and roots are 3 different words for the same thing. Okay? When do we use each? Well, if y equals f of x, that means you could have any polynomial function here, like let's say y equals x squared plus 4x minus 6, or maybe it's in factored form like the one we looked at first. Maybe it's y equals x plus 2 times x minus 4. The zeros are the numbers that make that function equal 0, okay? They will also be, when you graph, the x-intercepts. And how do you find them? Well, you set the equation equal to 0, and you find the roots. Roots just is another word for the solution, okay, or the value of the variable that makes that statement true. All right, so zeros, x-intercept, roots. That's what we're interested in helping us identify and draw graphs of polynomial functions. Okay. Good. If a polynomial function has a factor, bracket x minus a, that is repeated, if a polynomial function has a factor x minus a that is repeated n times, then x equals a is a 0 of order n. Okay, we'll get into this as we go along, but here's just a quick example. So if you had f of x equals x minus 2 times, in brackets, x plus 1, but we're going to square that last term, okay? So that actually means that you have x plus 1 times x plus 1. Then we would say, here's our zeros. We have a 0 at x equals negative 1. And this is order 2. So we have a 0 of order 2 at x equals negative 1. And at x equals 2, we have a 0 of order 1.
So what's in order again?
Basically, it just is identifying if that factor is being repeated more than once. So if it's a factor that's being repeated once, then the 0 is x equals 2, and it is of order 1, which we wouldn't really say, you just call it a 0. If the factor is repeated, then the 0 that satisfies this is x equals negative 1, but it's of order 2. And if you had a factor that...
It's just like the degree.
Basically, yep. If you had a factor of x plus 4 and it was repeated 3 times, then x equals negative 4 would be a 0 of order 3. It's just a way of identifying how many times that factor is repeated, because the behavior then of the x-intercept is going to be different.
So like the 0 is just the intercept root.
Correct?
And the order is just whatever power.
Right, and it's going to change what it does as it hits that x-intercept. It's either going to cross, touch, or squiggle. Order 1,
yeah.
order 2, order 3. But I think we're going to take those notes.
Oh, okay.
And
I couldn't tell why it mattered until you did the squiggles.
Yeah.
Now
Yep, we'll get there. Okay, so then we can say this is order 2, or you can call it a double root at x equals -1, but this guy is still order 1. Very typical, okay? So you have a picture there below with a couple of arrows, and it looks something like this, with the x-intercept, with the x-axis coming across like that. And basically we want to identify what's happening at each of these places. So you have an arrow pointing at this 0. By the way, this graph matches our equation here. This is the graph of f of x that we're working with. Okay, so we have a 0 here at -1. Maybe it doesn't match. Oh, it's different than the one that I drew. That's a bit confusing.
You're at -2 also.
Yeah, this is at -2 in the picture that you guys have. So that's kind of annoying. What we could do is we could change our signs here so that it matches up more nicely. If you could do that, that would be helpful, just so that we're all talking about the same thing. It's kind of annoying, but here we go. This is order 2, which means, sorry, this is order 1. Order 1, which means it's going to change signs. So if we're reading from left to right, this thing is going to cross into positive land. Okay, it's going to cross the x-axis and keep going. Yeah? So order 1 will cross the x-axis and keep going. The 0 here at x equals 1 is order 2. So it is not going to change signs. Okay? It is going to touch the x-axis and bounce back up. Okay, it's going to touch the x-axis and bounce back up. Let's make a little note of that so it's a little bit easier than what I have written here. But basically, zeros order 1 will do what? They will, maybe I'll just draw a whole x-axis along here. X. They will cross the x-axis. Okay? They'll either go from negative to positive or from positive to negative. Okay? Order 2, they will touch. They'll either go positive, positive, or negative, negative. But they will touch at that point. Zeros of order 3 will cross with a little dance. So they'll either go from positive to negative or from negative to positive. And these can simply be factors within a larger polynomial function. So it could, a complicated polynomial function could cross like this, could come back down and touch, could come back down and go all the way through and then come back up and touch, and then it could come all the way back up and do a squiggle. So you could have multiple x-intercepts, but this is just what each of those would look like according to the factor, the repeated factors that you have. Okay? Okay, so we're considering this same picture that we have been of the graph of y equals x minus 1 squared x plus 2. And it's great to be able to see for which intervals the function is positive and for which intervals it's negative. So here we can clearly see that it's positive from -2 to positive infinity, and it's negative to the left of -2. There's our x-intercepts. But we want to know how to determine it mathematically, so that if we don't have the picture of the graph, but we kind of know some of the factors, maybe we don't know all of the factors even, we can decide, is it positive, is it above the the x-axis, or is it below the x-axis? So right now it's easy, we can already see the answers that we're going to get to. But in order to determine positivity and negativity, to determine if the function is positive or negative, we can test some values. So basically, we want to test what's going on to the left of our most left x-intercept. We also want to check what's happening to the right of it, and that will tell us if it's, you know, touching, or if it's going through left to right, top to bottom, or if it's going through from negative to positive. Okay, so a little note: in order to test if the function is positive or negative, check algebraically what is happening on either side of each zero.
Since these are all orders of 1, it just like there's like very average squiggles.
This is order 1. This one is order 2.
Wait, it's ordered. Oh.
Okay, so here we go. We're just gonna learn how to test and check. We already know what's happening, but when we get to more complicated things where you have to draw, then you're gonna need this. So we want to know what's happening to the left.
All of them are exponents to the first degree. It's like,
This one's not.
oh no, I'm talking about the graph we're graphing. Like the x subtract 3, x plus 2, x plus 1 function.
We're not there. So
Okay.
you're right. That one's pretty straightforward, but that's not. That's just kind of a warm-up question that I didn't read. Yeah, it's just to help us think about graphs, how they would go up and down. So you could probably picture that one in your head pretty good. To the left of -2, and we're going to use x equals -3. Okay, it's just a value that is to the left of -2, and it's still in that interval where nothing is changing over there. And then we're also going to look at to the right of -2, and for that we're going to look at x equals -1. Okay, so we've chosen a point somewhere down here, an x value, to look to the left of -2, and all we're going to do is sub that in to our equation. Okay, so wherever you see an x, we're going to sub in -3. And then solve. I'm just going to do it quickly. -3 minus 1 is -4. Squared is +16. And then over here we have -3 plus 2, which is -1. So we have -1 times +16. It's -16. Okay, over here to the right, we're subbing in -1 for x. So wherever we see an x, we're going to put in -1. And what do we find out? We've got -1 minus 1, that's -2, squared is +4. And here we have -1 plus 2, that's +1. It's going to leave us with 4. So what we learned is that to the left of -2, the function is negative. To the right of -2, the function is positive. So there is a change of sign from negative to positive. So here f of x is less than 0, as in it's negative, and here f of x, that's the function, is greater than 0, that is, it's positive. Okay, that tells us it's going through. We're going to do the same thing for the point, the 0 at x equals 1. So to the left of x equals 1 and to the right of x equals 1. You guys got to tell me to zoom in. Here we can use x equals 0, and here we could use x equals 2 as a point of reference. So we take our original function, and anywhere we see an x, we're going to sub in 0. So we've got 0 minus 1 squared times 0 plus 2. This is 1 times 2, which is 2. Over here, we have subbing in 2 for x. So we've got 2 minus 1 squared and 2 plus 2. 2 minus 1 is 2. 2 minus 1 is 1. Squared is 1 times 4 is 4. So in both cases, it's positive. So it tells you that it doesn't change sign. Okay, that tells you right here that it's just going to touch down and come back up. Whereas this one, it tells us it's going to be down and then come up. Okay, good. That's just a tool that you're going to need as we move forward. So let's get to example 1. Example 1, analyzing graphs of polynomial functions. For each graph of a polynomial function, determine first the least possible degree and the sign of the leading coefficient, then the x-intercepts and the factors of the function, then the intervals where it's positive and the intervals where it's negative, okay? So we're looking at A. You have the picture there in your notes. 1. So tell me about the x-intercepts. How many are there?
There's 3.
There are 3. Are they all order 1, or is there order 2 and order 3 intercepts?
All order 1.
They're all order 1, okay? So we have 3 x-ints of order 1. So the least possible degree is 3. Okay, this couldn't possibly be linear, couldn't possibly be quadratic. It must be cubic or more. Okay, that's all we can tell from that. We can also tell its end behavior, because we can see it. Say end behavior is from what? Q2 to Q4. So what does that tell us about the leading coefficient? So we're trying to derive, we're finding things out about this just by looking at the picture. What do we know about the leading coefficient if we're going from Q2 to Q4?
It's positive. Negative.
So if you read from left to right,
I was thinking.
and we're going down,
It's negative.
must be negative, right? Good. Leading coefficient
Never mind.
is negative.
I thought the top ones were 2 and 4 for a second.
Okay, 2, the x-intercepts. and the factors. Okay, what are the x-intercepts? You can see them.
-5, 0, and 3.
-5, 0, 3. Okay, we'll always try to write those from left to right, chronologically. And that tells us that the factors then are x plus 5, x by itself, and x minus 3. Okay, these x-intercepts correspond with these factors. So if you know the x-intercepts, now you know that the function is made up of these factors. And if you know the order of them, which we do, then you know that they're only repeated once each. So there you have pretty much, not exactly, but you have a good portion of the function. You still don't know the leading coefficient. Okay, good. And then we can talk about the third thing. Says the intervals where the function is positive and intervals where it is negative. You're going to use the box that's drawn for you down at the bottom there. Okay, we have our intervals, and we're going to have the sign of f of x. So what are our intervals? Well, using bracket notation, we're going from -∞ to -5, because that's where some action happens. Okay, and we're not going to include -5 because we know it doesn't have a sign. It's neither positive nor negative. It's 0. Then we're going to go from -5 to our next point of interest, which is 0. Then we're going to go from 0 to 3. And then we're going to go from 3 to infinity. You don't have enough boxes. Well, from the graph, we can see what's happening. Is the function positive or negative to the left of -5?
What does that mean?
So the function is the red line.
Like it's positive?
Yeah. What about in between -5 and 0?
Negative?
Negative. In between 0 and 3?
Positive?
And from 3 to infinity?
Negative.
Okay, so the information that we get from that is where is it positive, where is it negative? That means it's positive for x belonging to the intervals -∞ to -5, and when x belongs to the interval of 0 to 3 exclusive. Okay, it's negative for x belonging to the interval of -5 to 0 exclusive, and the interval where x belongs to the values from 3 to positive infinity. For example B, which we are not going to do, but we'll run through it really quickly, you have 3 x-intercepts. 2 of them are of order 1. If you're looking at the picture in graph B, 2 of them are of order 1, and 1 of them is of order 2. Okay, so what you would find out is when you're doing your interval chart for that one, that at the 0 of order 2, there is no sign change. Okay, so the interval of positivity, negativity doesn't change at that point. Anyway, you could do that one on your own if you need to, but let's skip ahead here to example number 2. Oh, that's too quick. Example number 2. This time, instead of going from a graph to an equation, partial equation, we're going to go from an equation to a graph. And maybe I'll just jump ahead and do example B right away, okay? So example 2B, you've got y equals -2 times x minus 1 squared times x plus 2. And we are going to sketch a graph of each polynomial function. So what do we want to find out about it? Well, we want to find out what degree it is.
Second?
The whole function. What degree is it going to be?
Third?
It's going to be third degree because if this factor repeats itself twice and we were to expand it, we'd end up with one of the terms being an x squared term. And then this has an x term in it, and it's all being multiplied together. So you're going to end up with x cubed. You're going to end up with x times x times x in the expansion of this thing, okay? So what can we say? The product of factors will give an x cubed term.
Leading coefficient would be -2 because the x times x times x would leave you with just x cubed.
Thank you.
Right.
So therefore it's cubic. Leading coefficient. That's right. So basically if you want to determine the leading coefficient, this one is easy because the coefficient of each x term is just 1. But basically you'd take the coefficients of each x term, each term involving an x, and you'd multiply them all together. In this case, we just have -2 because you'd have 1x times 1x squared times -2, which would give you a leading coefficient of -2. So a little note, this is the product of all x coefficients. Notice it involves the -2 out front as well, even though it doesn't look like it's directly attached to an x, it is, right? Brackets indicate multiplication, so it is being multiplied by the x terms as well. So that one's -2. Then we have end behavior. Well, we don't have a picture to go off of, but we know that it's negative, and we know that it is cubic. So if you can picture a cubic, the cubic changes directions, but this one is negative. So we're going to start in Q2 and head to Q4. And note, it's a negative cubic. Zeros.
We have -2 and 1
We have x equals -2, and we have, you don't actually need x equals -2, you can just say the zeros are at -2 and 1. This is how we would write it if it was X-Intercepts. And last thing, how do we find our Y-Intercept?
It's just, there is no Y-Intercept.
Okay, so to find the Y-intercept, remember, of a polynomial function, you don't have to write this, but you've got, you know, say an x cubed term, and you've got an x squared term, and you've got a term with x in it, and then you have a constant. Okay? Constant represents the Y-intercept, because the Y-intercept occurs where x is 0. So that would be 0, 0, 0, and you'd just be left with the constant. So how do you get it from here?
What if it's -2 from 2 times -1?
Okay, that's close. That's part of it. We're going to actually multiply all of the non-x terms. So you've got, eventually, if you were to expand this, you would have a term that was built by getting 2 times -1, which is -2, times -2. Okay? So you would have, let's say, product of non-x terms.
Since we square the thing, there's 2 -1s, so it'd be -4, right?
Right, good job. So we'd be squaring that -1, which means we have 2 factors of -1, and we would multiply these guys out. So we'd have +2 times -1 is -2 times +2 is -4. So our Y-intercept there is -4. And you have a picture there. Let's quickly sketch it out, and then that will be the last thing that we do, apparently. Did you already sketch it?
Yeah. I actually sketched with negative 2 and then actually like erase it and put negative 4 there.
Okay, so we've got zeros at negative 2 and at 1. Okay, we know it's heading from quadrant 2 to quadrant 4. And we know that the 0 at positive 1 is order 2. So we might want to note that, order 2, which means it's just going to touch and go back to where it came from. So here we go. We're going to start somewhere up here. We don't know exactly what this thing looks like. Oh, we also know the Y-intercept. 1, 2, 3, 4. So we're going to touch and go through.
It's going to do
and it's going to be down here.
For the negative 1.
Well, it'll be lower. The vertex type thing will probably be lower down there. And then at 1, we're just going to touch and come back down.
That's what I meant. Vertex, max.
All right, so if you can get this key information from the formula, from the equation, then you can give yourself a sketch, and it gets a little more difficult as you go, but that should give you a good head start on your practice problems, and we'll wrap up this lesson another day. Example 2c, we are given the equation y equals negative, and then in brackets 2x plus 1 cubed x minus 3, and we're going to get a whole bunch of information here, starting with the degree. So remember, the degree is the product of x's. Anyone know what we're going to end up with? X to the power of what? So in that first one, we're going to have 3 factors of x, because it's raised to the power of 3, and then you're going to multiply by another factor of x. So you're going to be 4th degree. Okay, it's the power of x's. That's the word for that for us is quartic. They have our leading coefficient. That's going to be the product of all of the x coefficients. Go ahead and try and do that.
Negative 2? No, 4.
Keep going.
Negative 4.
So you're going to end up with 2 to the power of 3, which is 8, and then in negative.
Oh, 3.
So you're at negative 8 as a leading coefficient, okay? So I'll just write down what happened there. Basically, you have a negative 1 out front. Then you have 2 to the power of 3. And then you have 1 as the coefficient of the last x term. So you end up with negative 8 as the leading coefficient. End behavior. End behavior. It is a quartic, and it's negative.
Q2 to Q4?
So Q2 to Q4.
2 to 4.
No, sorry, 3 to 4.
Yeah,
Is that what you said?
Yeah, I started saying 3.
Yep, so whatever it does, it's going to come up and do something like that, potentially. Okay? And zeros and x-intercepts.
X-intercepts at negative 1 and positive 3.
All right, so we have, careful, it is the x that will make this factor 0 is actually going to be negative 1/2. Okay, so it's the opposite sign, and then b over a, negative 1/2. So if you multiply 2 by negative 1/2, you'll have negative 1 plus 1, which will make that whole bracket equal 0. So,
Okay.
so the way to do that, if you can't remember or if it's not going quick, you just say, okay, what's going to make that equal 0? And then you do algebra. You subtract 1 from each side, divide both sides by 2. X equals negative 1/2. So we have zeros at negative 1/2 and at 3. And that is then where our x-intercepts are. But we also want to note that this is, and maybe I'll erase that, note that this is a 0 of order 3, because that factor is raised to the 3rd power. And then last, Y-intercepts. Y-intercept. That's going to be the product of the constant terms, or you could say set x equal to 0 and then finish it out. So what we end up with is negative 1 to the power of 3, because this whole guy is 0. And this x is 0, so the last factor is just going to be negative 3. We can raise that to the power of 3. So we're going to end up with 1 times negative 3, which is negative 3, times negative. So a negative of that is going to be positive 3. Okay, again, how do you do that? You take this negative 1, multiply it by the constant here, which is raised to the power of 3 first, and then multiply by the constant here. And we end up with a y-intercept of 3. All right, we're going to look down at our graph. You guys have a big grid there drawn for you. Looks something like that. First thing we can do is mark our intercepts. So we can mark the x-intercepts. Both of them have an odd order, which means they are going to have a sign change from positive to negative. Okay, so we're at negative 1/2, which is right here-ish. And we're at positive 3, which is here. Okay, we know that we're going to kind of come up from here. All right, and we're going to be going down something over there. Okay, that's just in there to help gauge what I'm doing. Okay, we have our x-intercepts at negative 1/2 and positive 3. We know this is of order 1 and this is order 3, so we know that's going to cross from positive to negative or negative to positive in both cases. We have a y-intercept down here at 3, and so from quadrant 3, and it's going to end up coming back down in quadrant 4. We're going to come up, and this 0 is of order 3, so it's going to do this cubic thing. A little jiggy jog, and then we're going to hit our y-intercept. And you maybe wouldn't know this from the equation, but this one, the maximum is way up here, around 125, 130. And then it's going to come back down through our other x-intercept. Okay, and again, we label our graph y equals negative 2x plus 1 cubed, and the other factor x minus 3. What things did we know before coming into this? We knew our x-intercepts, we knew our y-intercept, we knew our leading coefficient was negative, so it's going to have our end behavior of Q3 to Q4, and then you do the best you can to sketch it. And if you're at home and you're really not sure what you're doing, you can always double check on Desmos. Okay, we've been talking about even functions and odd functions, but really we should be using the term even degreed function. So you don't need to write this, but if a function is, x to the power of 4, this is an even degreed function. Okay, here's another example. If we had 2x minus 1 to the power of 2, x plus 4 times x, this would be an even degreed function because you'd have two factors of x here, one there and one there. You multiply them together. Whatever this x term is, it's going to be x to the power of 4. That's even, okay? That's an even degreed function. Same goes true with odd degreed functions. You can have an odd degreed function if the product of all of the factors of x, if you end up getting an x to the power of an odd number, then it's an odd degreed function. But what we need here are examples of an even function. So we're going to make a distinction here. We're looking at an even function is an even degreed function in which the exponent of each term is even. So an even function is an even degreed function in which the exponent of each term is even. Okay, you have a picture of that provided for you. It looks like a quartic there. But what do we notice about the picture is that function, that graph, is symmetrical. Okay? It's symmetrical. The value of the function at negative a, x equals negative a, is the same as the value of the function at x equals a. Okay? A couple of other notes that we can write about this because we're going to have to test whether or not this is true in certain situations. So the first thing to look for, if you have the equation, is every term in the equation even degreed? If it is, then you know right away it's an even function. If it's not, you know right away it's not an even function. Okay, there are other ways to test. This satisfies the property, like we drew on our graph, f of negative x is equal to f of x. Okay, so it's symmetrical about the y-axis, which is our next point. Symmetrical about the y-axis. We're going to write a very similar note about odd functions. Okay, you should mark, maybe underline your new vocab. This is an even function. In order to distinguish between, we might call it like a even function or a really even function, or just because often we mix up, we'll use the word even to mean even degreed. So we'll just have to be more careful about that. Okay. In the same way, an odd function is an odd degreed function. An odd function is an odd degreed function in which the exponent of each term is odd. The exponent of each term is odd. Okay, that is an odd function. You can see the picture that goes with that as well. What's true about it? I can do it on the graph here, but the value of the function at x equals negative a, so here, is the same as the value of the function, is the opposite of the value of the function at x equals a. Okay, so
it's equal to negative f equals a.
Correct, which is exactly what we're going to write. So this one satisfies the property f of negative x is equal to negative the value f of x. And this has point symmetry or rotational symmetry about the origin. Okay, so just a very quick recap on something we wrote originally. The odd function is an odd degreed function in which the exponent of each term is odd. So in order for it to be an odd degreed function, just the first, if your terms are ordered in descending powers of x, just the term with the highest power of x needs to be odd, right? So a cubic is odd, a quintic is odd, linear is odd. no matter what else comes after that first term. In order for it to be an odd function, there can be no even degreed terms. Okay?
But like,
In example 3, we use those properties that we just learned about odd and even functions to identify whether or not there is symmetry. So without graphing, we're going to determine if each polynomial function has line symmetry about the y-axis, in which case it would be an even function, point symmetry about the origin, in which case it would be an odd function, or neither. Okay? Example 3a. We have f of x equals 2x to the power of 4 minus 5x squared plus 4. What do you think?
it's symmetry about the y-axis.
Okay, so we know there's symmetry about the y-axis, which means it's what kind of function?
It's an even function.
Even function. Okay, here we can tell just by looking at it. That was really easy.
So it's a term for the function if everything's even.
Even.
Okay.
The term for if not everything is even degreed function.
Oh, even degreed.
So it's named after, the degree is named after this first term. This is an even degreed function because the leading term is x to the power of 4. 4 is an even number.
Okay.
It's an even function because all the rest of the terms are also even degreed terms.
Yeah.
4 being 4 times x to the power of 0.
Right.
Okay, so this is an even function, which means, what does it mean? That it has line symmetry about the y-axis. Okay, and for the sake of practice, we're going to actually check, we're going to use our property. We're going to check that f of negative x is equal to f of x. Okay, so we don't need to put in any specific numbers. We don't need to put in, x equals -2 and x equals 2, or x equals 1 and x equals -1. Okay, that wouldn't help us. If it verifies one point, doesn't mean that it's true. Okay, so we're just going to sub in everywhere we see an x, we're going to sub in -x. And if we come out at the end after simplifying it with the same thing that f of x equals, then we know that it does verify this property. So here we go. We're going to take this right side of the equation here, and everywhere we see an x, we're going to put in a -x. So instead of 2x to the power of 4, we have 2 times -x to the power of 4 minus 5 in brackets -x squared plus 4. Okay, and this is really helpful to see how it's going to work, because you know that if you raise a negative value to a even exponent, all it's going to do is take away the negative sign, right? So we've got here, the 2 is not raised to the power of 4, only -x is, so we have 4 factors of -x. 4 negative factors becomes a positive, x to the power of 4 is x to the power of 4. Next term, 5 times, and I have -x squared. Well, negative times a negative is positive. That just leaves me with x squared, and nothing changes in our last term. And you can quick double check. 2x to the power of 4 minus 5x squared plus 4 is the same as we have up there. So f of -x does indeed equal f of x, verifies the property for an even function. Okay, that one was really easy to do because we could see it just from the equation in standard form. Next, B has f of x equals -3x to the power of 5 plus 9x to the power of 3 plus 2x. Is it special?
It's point symmetry about the origin. I can tell by looking at it.
Yeah, it is an odd function.
Odd function.
So it does have point symmetry about the origin. And this time we're going to check using the property for odd. So we're going to check that f of negative x equals negative f of x. So how do we do that? Well, everywhere we see, this is going to take two calculations, but for the first one, f of negative x, we're going to take our original equation, and everywhere we see x, we're going to plug in negative x. And then we're going to simplify. So here we have negative x, 5 factors of negative x. Well, 5 negative factors is a negative. So this is just going to stay negative x to the power of 5. And then we're going to multiply it by negative 3. So you're going to have positive 3x to the power of 5. In our next term, we have 3 factors of negative x. That gives us negative x cubed. And we're going to multiply by 9. So we have negative 9x cubed. And our last term, we have 1 factor of negative x times 2. So that's negative 2x. Okay, that we can clearly see that's different than what we had here. Okay, but we haven't confirmed anything because our property actually says that this needs to be equal to negative f of x. So we're also going to calculate that. Well, how do we do that? Basically, we take the whole original equation, the right side of it, expression, and then we put a negative in front of it. So we've got negative, and then in brackets, negative 3x to the power of 5 plus 9x cubed plus 2x. And you know what a negative sign does out in front of anything? It makes every term negative. It flips the whole thing around. So we get positive 3x to the power of 5 minus 9x cubed minus 2x. And now we can see that those things are equal. It checks out. It is indeed an odd function. In C, we have a function. It is not in standard form, so we're not just going to be able to look at it and say what it is. We're going to have to test our properties. Now, which property are we going to try? The one for even numbers or the one for odd numbers? So what you would do is you simply count the powers of x. There's 1 factor of x, 2 factors of x, 3 factors of x. So this is a cubic. Okay, that doesn't mean that it is an odd function. It is an odd degreed function, but we don't know if it's an odd function. Cubic, therefore, may be odd. So we're not going to expand into standard form. We're simply going to check the property for odd functions. We're going to see if f of negative x is equal to negative f of x. Okay, so in order to check, we're going to sub in negative x anywhere we see x. I'm going to work through this one fairly quickly. Again, just subbing in negative x anywhere that I see an x and making sure I copy everything else down properly. And then I'm going to expand this. Okay. I'm going to factor out the negative 1 from each factor, and that might make it a bit easier. Actually, we'll just do this in bits and pieces. So I'm just going to multiply these first two together, and I get negative 2x. And then I can do this next one probably in my head as well. So we've got negative x. This is just foiling, right? So I expanded this with that one, and now I'm going to FOIL these guys. First times first, outside times outside, inside times inside, last times last. But here we go, we have negative x squared. Then we're going to have positive 2x's and negative an x. So we're going to have positive x, and then we're going to have negative 2. 1 times negative 2 is negative 2. And now I can distribute this negative 2x to all of 3 of the terms inside my trinomial here. It's okay if this is going too quick. This isn't really what this lesson is about anyway, but it's just a helpful part. It's algebra. You should be able to do this. Okay, so we're looking at positive 2x cubed, negative 2x squared, and positive 4x. And we're going to see if that is equal to negative f of x. So how do we do negative f of x? We simply put a negative sign out front of this whole thing and plug in 2x. Not that. X plus 1, x minus 2, close bracket. And again, I can expand this in the same way. So I'm going to FOIL out this back half here, x plus 1 times x minus 2. So I'm going to leave the front intact. Gives me x squared minus x minus 2. Then I'm going to expand out this 2x into there. Gives me 2x cubed minus 2x squared minus 4x. And then I can distribute the negative sign to all of my terms. We end up with negative 2x cubed plus 2x squared plus 4x. Okay, are they equal? They look kind of close, but they are not equal.
Negative.
Okay, so therefore no odd function and no point symmetry.
I thought it wouldn't count as an odd function.
Example D, we're just going to talk about briefly. We have f of x is x to the power of 6 minus x to the power of 3 minus plus 6x squared minus 4. The leading term with the highest power of x is even degreed. So the function is even degreed. But what else do we see? We see some odd degreed terms in there as well, 1. So this does not have line or point symmetry. It is neither odd nor even. Okay, good. Last little note. I think you have some space there. Yep, you have a little picture at the bottom of page 16 in your notebook. When a constant term is added to an even function, when a constant term is added to an even function, comma, the function remains even. How do we know that? Well, the picture demonstrates that adding a constant just moves it up or down along the y-axis. Okay, it doesn't move it left or right at all. So if your original had line symmetry and you move it up, it's still going to have line symmetry. If you move it down, it's still going to have line symmetry. Okay. The constant doesn't change anything. Another way to think about that is a constant is really just ax to the power of 0. X to the power of 0 is 1, leaving you with just the coefficient, which is the constant. Good. That is the end of lesson 1.3. Practice problems are on page 39. They are numbers 1 through 9.